Hey guys, I hope you're all doing good. By this time, you might have simulated several systems in CONVERGE. We started with a simple channel flow, and then we simulated backward step flow problem, the elbow problem, the shock tube problem, and so on. Right? So by this time, you are kind of aware of the features that CONVERGE supports, but you might not necessarily know how these features work in the backend. And this is where the theory lessons come into play. As you are working on the projects or assignments that we have provided you, take a look at the theory section, because at this point, since you've already done so much with CONVERGE, it's going to be very easy for you to understand the theory, right? And you will also be able to remember it. So we are not going to be covering all the theoretical concepts in just one lecture. We are just going to split it into multiple lectures so that it is easy to understand and watch them, and if you have any questions, get back to us. So today we are going to be spending a little bit of time understanding the capabilities of CONVERGE, and then once we have talked about several case studies, we'll directly jump into understanding the computational mesh that CONVERGE creates and how that is different from other softwares. And then you will learn an important concept called load balancing, all right, which is related to parallel processing. And finally, we'll talk about regions. So first of all, why did we choose to use CONVERGE? CONVERGE is a general purpose CFD package, which means it can be used to analyze flow through any system. And one of the reasons why CONVERGE is so popular because it has a fully automated mesh generation process and is extremely suited for complex geometries that actually move in a complex way. All right. And on top of that, CONVERGE also has something called as adaptive mesh refinement. With adaptive mesh refinement or AMR, you don't have to guess where the mesh resolution needs to be higher or where the mesh resolution needs to be lower. The solver is going to figure it out automatically by monitoring the solution during runtime. In addition to this, CONVERGE can also be used to simulate reacting and non-reacting flows. Reacting flows are one where chemical reactions take place, and CONVERGE supports that as well. And finally, any industry standard simulation tool must be able to run in parallel. You might have already run a couple of simulations in parallel using MPI. Now with CONVERGE, you can run simulations with more processors if required. And it also comes equipped with state-of-the-art physical models. Now in this lecture, we are not going to be talking about the physical models. That is meant for a different lecture. So now let us start by looking at some case studies. So here we are actually looking at results that were obtained from a diesel engine simulation. Okay, so this study was done by Caterpillar and Sandia National Labs. On the left hand side, you are looking at pressure trace. So this is how pressure inside your combustion chamber changes. All right, you can see that initially pressure increases during the compression process, and once combustion takes place, there's a rapid increase in pressure, and then there's the expansion stroke. Now you can see that the measured value, which is the experiment value, and the predicted value, which is from CONVERGE, match exactly, which is actually quite promising, right? If you get such a good match, then you can make all your design changes in CONVERGE and you can just simulate it and look at the trends instead of worrying about setting up the experiments. On the right hand side, you actually have NOx. So NOx is one of the major pollutants that people care about. Again, we are actually comparing the measured NOx and the predicted NOx. And on the x-axis, we actually have SOC, which is nothing but start of combustion. And you can see that the match is quite good. You are looking at NOx in ppm, all right? So this type of a match is extremely encouraging and it is quite hard to get. And here's the reason. Now, when you take up a system like internal combustion engine, you need to get the following things right. You need to get the fluid flow correctly. You need to get the turbulence correct. You need to get the geometry correct. You need to get the combustion correct. And you need to get the emissions correct. Only if you get all of these things correctly, your final results would be right. Now let's take a look at a different type of engine. Now this right here is a gasoline engine, and to be specific, this is a GDI engine, gasoline direct injection engine. Again, this study was done by Argonne National Lab, and here you can look at something much more interesting. I would like all of you to focus on the left hand side plot. So here you are looking at a GDI engine which was run with 0% EGR. EGR stands for exhaust gas recirculation. It's a technique that is used to lower NOx emissions. So here the black dotted line is your experimental data, and you can see that there are a lot of scattered points. What are these? Now what happens is when you run an engine experiment, you run it for multiple cycles. A cycle is 720 degrees, correct? For each and every cycle that you run, we are actually looking at the peak pressure that was obtained from experiments. Now if you take all of those peak pressure data, that is what is being plotted as this scatter plot. You can see that the peak pressure varies quite a bit, and this is what you call as a cycle to cycle variation. Now this is a huge problem in GDI engines because this actually produces non-repeatable combustion pattern, which we want to avoid as much as possible. So one of the things that people try to do is they try to simulate it to see why it occurs. Now here the colored curves are all simulation data. Okay, so what's happening is CONVERGE is able to predict how the peak pressure changes for each and every cycle. So in this case, we have run the simulation for 21 cycles. Now, when I say 21 cycles, each cycle is 4 strokes, right? So you run it for 21 cycles. And you can see that the variation is getting captured. Now, this type of a validation is extremely impressive because cycle to cycle variability is one of those things that people are really trying to understand and are trying to reduce. On the right hand side, you have a similar looking plot. Now this time the case was run with 18% exhaust gas recirculation. Again, you can see that CONVERGE is able to very well predict the trend in peak pressure, right? Which is quite impressive if you think about it. And in order for a solver to get this correctly, it needs to get turbulence correctly, it needs to get the flow correct, it needs to get the geometry correct, the spray correct, and the emissions correct. So if you think about it, CONVERGE is kind of predicting all those things correctly, and that is why the end results also look great. Okay. Finally, what is CONVERGE being used for these days? Now industry is tending towards a technique called as a pre-chamber ignition system. So pre-chamber ignition systems help us reduce specific fuel consumption, and so these are modern systems that are still being developed. Now here you can see the CAD model of a pre-chamber system. You have a pre-chamber and a main chamber. Now here we are able to see how the flame actually propagates inside this pre-chamber, and this is actually quite impressive. On the right hand side, you still have the pressure versus crank angle diagram, and you can see that the pressure trace both in the pre-chamber and the main chamber match very well. Getting these type of validation data is extremely hard, and if a simulation tool is able to do it, then you can actually use that simulation tool for predictive analysis. I hope at this point you are able to appreciate the capability of the tool and what it can do. So finally, let us take a look at a much more fundamental problem. Basically, just spray and turbulence. These are problems that are extremely hard to capture accurately. Now here what you're actually looking at is called as a vaporizing spray problem. So what's happening is, you can see that you have fuel spray coming in, and as the fuel spray comes in, it basically goes into the chamber and it starts to vaporize, and it gets this characteristic shape. On the right hand side, you have simulation data. Don't worry about this term DS-0.5 mm. This is basically a turbulence model that's available in CONVERGE, and 0.5 mm refers to the mesh size. So here you can see that the mesh is really large, and as you move from left to right, the mesh is becoming finer and finer. And as you can see, when the mesh becomes finer, we are able to capture the vaporizing spray behavior very, very accurately. Now you can say that this last set of 4 images are very similar looking to the experimental data. This is how capable CONVERGE is. You are able to compare these fundamental quantities, and if you think about it, that makes sense, right? Only if your fundamental concepts are correct, only if those fundamental quantities have been captured correctly, your global quantities would match. Okay, and this is a strong example for that. So similarly, on the right hand side, we are actually plotting something called as the liquid penetration length. What does that mean? So when spray is getting injected into the combustion chamber, after some time it starts to vaporize. So because of that, the liquid portion of the spray has a maximum length, which is called as the liquid penetration length. And you can see that here the x-axis is time and y-axis is liquid penetration length. So initially the fuel comes into the combustion chamber and it keeps on penetrating, but after some time it starts to vaporize. It starts to vaporize in such a way that its liquid penetration length is more or less fluctuating. So you can see that here the liquid penetration length is about 10 millimeters. And the black line, that is your experimental data. So you can see that we are really close. Similarly, in the bottom image, we are looking at vapor penetration length. So this is basically the extent to which the vapor is penetrating into the domain. And you can see that that is much more larger than the liquid penetration length, which makes sense. Now, in addition to simulating flow, combustion, and emissions, CONVERGE can also simulate heat transfer in the solid side. So one of the things that people do is they run conjugate heat transfer simulations, where you're running both fluid flow simulation and solid flow simulation in a coupled manner. By doing these type of simulations, you can actually calculate the temperature distribution in your entire cylinder head block. This helps a lot because that is going to be the boundary condition for your FEA analyst. Now that we have looked at several case studies, I hope that you appreciate how powerful the tool is. Now let us take time to understand the different blocks that make up this particular software. We are going to start with mesh generation because mesh generation is what sets CONVERGE apart and helps CONVERGE implement a lot of physical models quite easily and accurately. So unlike other CFD codes, CONVERGE maintains the original surface definition with high fidelity, meaning accuracy, such that the volumes and areas are constant regardless of the mesh resolution. What does that mean? So let me just minimize the screen and go to a different interface. So in this image, you are looking at inside a combustion chamber. This right here is a piston, and this is going to be the cylinder head. This right here is the liner, and as I said before, this is the piston. Now you can see that I have three different configurations, right? So for example, in the first image, you can see that the mesh is uniform, right? All the mesh sizes are completely the same. Whereas in the second image, there is refinement in certain areas. The mesh is smaller in certain areas than the other. And in the third image, the mesh is quite different. It is quite fine in certain areas and it's big in certain areas, correct? Now, the first point that we are trying to make is, it doesn't matter how many cells you have to represent your geometry, the volume will always be the same. This is not the same in most cases. Now, this is not true in most of the CFD applications out there. So for example, if I have a circle like this, and if I try to mesh it in CONVERGE with just 4 mesh points, you can see that I have 4 cells, right? So 1, 2, 3, and 4. Now let us say that I calculate this volume and it's going to be V1. Now let us say that we set up a second case where we have more cells, maybe something like this. All right, so here we would at least have 20 cells, right? And let us say the volume here is V2. Now in CONVERGE, V1 will always be equal to V2. If you take a look at other softwares, depending upon the number of mesh points, your entire surface might get approximated. For example, if you just have 4 points, you will actually end up with a shape like this, which is not even a cylinder. If you increase the number of points, you will slowly start recovering the cylinder shape. By the time you actually get to a very realistic representation, you might have to use a large number of cells. Again, this is just an exaggeration. Modern softwares can handle this in a much better way, but I'm saying that there are still a lot of softwares which would give you different volumes when the number of mesh point changes. Okay, and when you're running a simulation, especially an IC engine simulation or a gas turbine simulation or external aerodynamic simulations, you need to make sure that the volume is kind of the same irrespective of the number of mesh points that you have. The second point is that the solver and meshing algorithms are tightly coupled, which means there is no mesh file that the user has to create. The solver is going to create the mesh automatically each and every time step, and based upon the flow conditions that come out of the solver, the mesh is going to be modified accordingly. So this gives you a consistency, right? For example, in ANSYS, you have to create the mesh before the simulation starts and the user creates the mesh. So depending upon the engineer's intuition and skill level, the mesh that is getting generated might be good or bad. Whereas in CONVERGE, since the solver dictates the mesh generation process, you can get consistency across different engineers, which means it's much easier to do things like grid dependency tests. Alright, so how does CONVERGE do it? CONVERGE automatically generates a body fitted volume mesh using cut cell Cartesian technique. Now this method is patented to CONVERGE, and because of this, CONVERGE can produce really high quality orthogonal hexahedral cells, which is extremely ideal for solver algorithm. Okay, what does this mean? Well, you might have heard of different types of meshes like tetrahedral meshes, polygonal meshes, and so on. Out of all these type of meshes, your Cartesian mesh or hexahedral mesh is going to be ideal for the solver. It reduces the errors in your discretized equations, meaning with just a few amount of cells you will be able to get the right answers. Alright, so this is the case with the interior cells. Now the cells intersected by the geometry surface are cut by the surface to form arbitrary sided polyhedras. Okay, and we will look at polyhedras in a short amount of time. And because of these concepts, your volume is the same irrespective of your mesh size. And also you're getting a large number of high quality cells. For example, this right here is a mesh that CONVERGE generates. Let us take a look at this a bit more closely. So in this image, you can see that this right here is what you call as a hexahedral mesh. Now this looks like a square, but in 3-dimensional, it's going to look like a cube. All right. And these type of meshes are preferred by CFD solvers, okay, because they are really perfect. They have this really nice right angle, which means you can compute derivatives, you can compute fluxes quite easily without making a lot of approximations. Now on the other hand, if you look at this particular cell, this is what you call as a cut cell. Now you can see that it's cut in such a way that it represents the boundary accurately. All right. So if you remember, when you start with CONVERGE simulation, right, you load a STL file, correct? When CONVERGE creates the cut cell Cartesian mesh, it uses the information from the STL file to create these cut cells. Now these cells are called as polyhedras. Just like you have polygons in 2D, polyhedras are 3-dimensional structures which can have multiple faces. So for example, in this particular case, if it is 3D, for example, it can be like a wedge. Similarly, you can have more complex shapes. Now, an interesting thing that occurs while setting up a CONVERGE simulation is called a cell pairing. What does that mean? So for example, here you can see that you have one cell. You can see that you have a really small cut cell, correct? Now here is another example where these arrows are there, the red arrows are there. You have 2 cells. You can see that I'm coloring all the meshes by their volumes, correct? Now this cell definitely needs to have a much more lower volume than this cell, correct? But why are both these cells colored by yellow, right? And yellow means the volume is much higher than the green, right? So you can see that inside the volume is green, and in these 2 cells the volume is yellow, which means it's much more higher. This is called a cell pairing. So whenever you have a cut cell, for example this right here, this little triangle, let us just call it a cell 1, and this is called a cell 2. So cell 1, the volume of cell 1, if it is less than 30% of the volume of cell 2, then these 2 cells get attached to each other. This concept is called a cell pairing. Now the reason why you do this is, if your cell size is very small, because of the CFL criteria that you have, your time step is going to be extremely small, and hence you have to combine these smaller cells to form larger cells. If you don't do that, your simulation will be extremely slow. If you do not understand what CFL means, don't worry, we'll be having dedicated lectures for that as well. So let me just go over the slides to make sure that I haven't missed anything. So first, CONVERGE trims the cells at the intersecting surfaces, which results in some irregularly shaped cut cells, which are also called as polyhedras. If the volume of the cut cell is less than 30% of the volume of the original cell, then CONVERGE combines the cut cell and the adjacent cell that shares the most cell face area with the cut cell. Okay, so that is just the pairing algorithm. And then finally, the center of the adjacent cell becomes the volumetric center of the combined cell. So what they mean by that is, in this particular cell, you have 2 cells, correct? When you combine them, you still retain the cell center. So when you combine them, you say that the center of the combined cell is basically equal or same as the cell center of the original cell. And finally, the original cell and the cut cell share transport quantities like velocity, temperature, and pressure, which means all those quantities have the same value in both of these cells. All right. Next, we are going to be talking about adaptive mesh refinement. AMR automatically increases the grid resolution based on curvatures in field variables. What does that mean? So let's actually take a look at this picture in a much more closer detail. So this right here is actually the top view of a combustion chamber, and you're actually looking at the flame front. So here you can see that there's a lot of interesting structures, but more importantly, I want you to pay attention to the cell size here, right? Maybe I'll use a different color. Let's just make it a bit more thicker, okay? So for example, if you look at the mesh right here, this is your base mesh, correct? I'm pretty sure at this point you know what base mesh is. This is basically the base grid that you set up. And then if you look at the mesh here, it's much more finer, correct? Based upon the embed level that you set. And the way this happens is, CONVERGE is actively looking at the second order derivative in flow quantities. It can be temperature, velocity. Basically, it can be a scalar field or it can be a vector field. So the quantity is going to be something like dou square phi by dou x square, and it's going to be multiplied by delta x square by 24, something like that. I'll show you the exact formula later. So what's happening is each and every time step at each and every computational mesh, you are monitoring this quantity. This right here is what you call as the subgrid scale. Now, if phi is actually temperature, then this would be called as the subgrid scale temperature. If v is going to be velocity, then it's going to be called subgrid scale velocity. Now you might have seen a window that's being shown on screen. This is the AMR configuration window, and if you pay attention, there is a parameter called SGS. This is what we are trying to define right now. Now based upon this SGS value, and now let us say that we are setting up SGS for velocity. If the velocity SGS is greater than 1 meter per second, then refinement is going to take place. If not, it's not going to take place. So this gives you a systematic and consistent way of refining the computational mesh, which you can apply for all sorts of simulations. And that is the power of adaptive mesh refinement. It is not relying upon the user's intuition or skill level. It is completely based on math, and that is going to give you consistent results over time. All right, so coming back to the slide, we know that AMR works based upon the curvature, which is nothing but the second order derivative in the flow quantities. AMR can be permanent or it can be activated at specific times. What does this mean? You can actually have AMR present from start to the end of the simulation, or you can start it at a particular time and end it at a particular time. You have all the flexibility that you need. Now, in addition to this, AMR can also be activated region by region. So if you have multiple regions in your domain, you can have AMR in only just one region. And then finally, AMR can be applied on both scalar and vector quantities. Now, depending upon the problem that you solve, your AMR criterion and the AMR variable can change. All right, so here's the general theory. So the idea is that, CONVERGE calculates the subgrid scale field using this particular formula. So phi dash is equal to phi minus phi bar. Now, phi dash is the subgrid scale field. All right, so this is your SGS field, okay? And phi is the actual field and phi bar resolved field. Now this phi is the most accurate value, the theoretical value, and phi bar is the value that you are resolving, meaning your computational mesh is resolving. And phi bar is the value that you are resolving with your computational mesh. So this is basically, you can think of this as the most accurate value for phi. For example, if phi is temperature, then this is going to be the most accurate value for temperature that you get. And phi bar is the approximate value that you get with your computational mesh, and that is T bar. So when you subtract these two, right, there is a small difference, and that difference is called as the subgrid scale value. All right. Now your subgrid scale value can be obtained by truncating an infinite series, and you will come up with this expression. And you can see that this kind of makes sense. When your computational mesh is smaller and smaller, right, which means dx is getting smaller and smaller, which means phi dash tends to 0, right? So if phi dash tends to 0, that means that your phi bar is getting more closer to phi, which kind of makes sense. When your computational mesh is smaller and smaller, you don't need to worry about the subgrid scale parameter. It is going to be smaller because you are resolving most of it. The next important thing that we are going to be talking about is running simulations in parallel. Now, for the few simulations that you've already run, you might have used something called as MPI run, correct? What is that? Well, first of all, CONVERGE is a parallel solver, which means it uses MPI libraries to parallelize different parts of its code so that it will run in different processes and across even different systems. Why do you need to do this? Well, if you take a look at modern engineering simulations, they are run with a large number of cells. Now, a typical internal combustion engine case is going to take around 1 to 2 million cells, and a typical gas turbine case is going to take 7 to 8 million cells. A typical external aerodynamic simulation case is going to take 20 to 30 million cells easily. All right. Now, when you have these many number of cells, you can't run the simulation in a single processor. It's going to take several months. So what you do is you distribute the calculations to different computers or different processors, and this is called as parallel simulation. Now, when you're simulating cells to different computers or processors, you need to take care of something called as load balancing. Now, let me explain that. So here I'm going to give a simple example. All right, so the example that I've planned is quite simple. So let us say that we have 4 pages, okay? And our objective is to read all these 4 pages together. So what we have to do is, let us say that we have 4 people. Then what I can do is, I can just give each one of them a single paper to read, and that is what you call as a parallel processing. That is, if each of them is going to take 1 minute to read a paper, in just 1 minute, I will be able to read 4 pages. Because all the 4 people can do it together without talking to each other. They can do it in parallel, all right? Now, if there is just one guy who is reading all the papers, it's going to take 4 minutes, correct? Because he has to do it sequentially. This is what is called a sequential computing. Now, there is an important concept called load balancing. What does that mean? Now, in the same example, let us say that you have one paper that has a lot of text, maybe 2000 words, okay? And then the second paper has 500 words. The third paper has only 10 words, and the fourth paper has 1000 words, all right? And you still have 4 guys reading it. Now, what's going to happen? Well, first, you are going to have the third paper finished because that is going to take the least amount of time. So this guy will finish first, and then he's just going to be idle, correct? Which means this guy is not being used. Then this guy is going to finish, and then they are not going to be used, and then the third guy is going to be finished, and then he's not going to be used, and then finally the fourth guy is going to finish. This right here is called load balancing. That is, even though you had 4 people to read, you are not utilizing them correctly, right? Because you have this particular processor, right? If we assume that all of them read the pages at the same amount of time, and let us say that the third guy takes 5 seconds to read 10 words, then how long will the first guy take to read 2000 words? It's quite simple, right? It's just going to be 5 seconds multiplied by 200, right? So this is going to take 1000 seconds. Now that's bad because in total, I have 3560 words, correct? And if I'm reading this with a single user, now if I just ask a single user to read all of these 3560 words, is going to take 5 seconds to read 10 words, correct? So which means to read 3560 words is going to be taking 3560 multiplied by 5 divided by 10, correct? And this is going to be equal to approximately 1700 seconds. So this right here is the amount of time that it's going to take for a single person. Now, if this problem was parallelized perfectly, then in order for 4 people to read it, the total time is going to be approximately equal to 1700 by 4, right? So that's roughly about 400 to 450 seconds, right? That's it per person. On the other hand, here you can see that the third person is becoming idle after just 5 seconds. So this is where load balancing comes into play. So what I can do is, after the third user has completed reading the third page, I'm going to divide the first page into 2 pages. Okay, so we have 1000 words and 1000 words, and I'm going to split the work so that I can engage the third person again. And I need to keep this process iteratively so that at any moment of time, all the 4 people are working towards the problem. This is called as load balancing, and it's extremely important. Now, if you have poor load balancing, that means that you are wasting away computer power, right? Some of the processors are just sitting idle, and you don't want that. So coming back to these slides, most engineering simulations are too large to run on a single processor and thus are run in parallel. Parallel computing requires splitting the computation among many processors, all of which must communicate with each other. The overall simulation speed is limited by the slowest processor or by the processor that has a large number of work to complete. Computational cells solved in CFD solver are load balanced separately from those cells solved in combustion solver. Okay, so for example, you might have seen a parameter called parallel scale. This is an important parameter which controls how load balancing takes place. So for example, in the image on the right hand side, the black cells are the cells that are available in your mesh points. The black cells refer to your mesh. Okay, so you have so many number of mesh points. Now what happens is, when you set your parallel scale to -2, you basically get 4 blocks. What is the formula? Well, the formula is quite simple. The block size is going to be base grid multiplied by 2 power parallel scale. Since parallel scale is -2, 2 power -2 is 1 by 4, right? So your entire computational mesh gets divided into 4 blocks. Now if you have only 4 processors, each block can be taken up by a particular processor. That's the idea. On the other hand, if you have more processors, for example, if you're running simulations in a laptop, most likely you just have 4 processors. In my case, I have a workstation which has 16 cores. So what I would do is I would set up my parallel scale to -1, right? So this way I have more number of blocks, which means each processor can work on a particular block. All right. So let me go over the contents in this slide. Okay, so Converge forms parallel blocks for partitioning from a coarse-based grid. Okay, parallel blocks are distributed in contiguous groups to the processors. The load balancing algorithm, which is MATIS, redistributes the parallel blocks to minimize communication and equalize the number of cells. Load balancing is performed throughout the simulation to account for adaptive mesh refinement and embedding as well. So here's an important thing that you need to understand. For example, in scenario A, I have just 4 blocks, right? So if I just have 4 blocks, even if I have 25 computational cores, I'm not going to be using them because Converge is load balanced based upon blocks and not cells. So if I have 4 blocks, the maximum number of computational processors that I can use is 4. So if you have more processors, you need to make sure that you have more blocks so that Converge can play with the load balancing. So in this example, say that you are running the job with 4 processors, correct? Then what's going to happen is, you can see that in block number 1, I have 55 cells. Block number 2, I have 13 cells. Block number 3 has 16 cells, and block number 4 has just 7 cells. So this is very similar to the paper example that we talked about earlier. In this case, processor 1 is going to be a bottleneck because it has large number of cells to process. It's going to take the largest amount of time. On the other hand, in the same problem, if I increase the number of blocks, then I have a much more finer granularity. Meaning what I can do is for processor 1, I can just give 3 blocks. The blocks with 16 cells, 4 cells, and 4 cells. So that's going to be 24 cells for block number 1. And for block number 2, we are going to be giving 6 blocks. For processor number 3, we are going to be giving 6 blocks. And for processor number 4, we are just going to have 1 block. So in total, we just have 4 processors, but now the cells are much more comfortably divided, which means in the second scenario, your simulation is going to run faster. Okay, whereas in your first scenario, your simulation is not going to run faster. So this is the idea behind parallel scale. All right, and you might recall this particular window, right, which contains simulation time parameters. And here you will be setting up something called as parallel scale and the number of cycles between parallel load balances. So when you're running a simulation in Converge, you would have seen that the iteration number is getting printed out. After every 100 iterations, load balancing is done. Okay, so these are important numbers, and typically the default numbers work very well, but sometimes when your problem is much more larger and when you need to run it on larger number of computers, you need to set up the parallel scale accurately. The final topic that we're going to be talking about is regions. So just like you have triangles which you collect together to form boundaries, you can actually collect boundaries together to form volumetric regions. Why do you need that? For example, this right here is a port fuel injected engine, and we are dividing that into 4 regions: region 1, region 0, region 2, and region 3. Right? Why do we have to do this? Well, regions are useful because you can actually control the flow between regions. So for example, when the intake valve is closed, there should not be any flow between region 0 and region 3, correct? This can be done by something called as events. When we were setting up the shock tube problem, I talked about events briefly, right? With events, you can actually stop the flow occurring between 2 regions. And it's very useful in cases like internal combustion engines. And similarly, what you can do is you can look at output results for each region, which means I can just look at the pressure in region 0, which is nothing but the pressure in the combustion chamber. Why is this important? When people run experiments on engines, they are able to measure pressure inside the combustion chamber. Now, from a simulation point of view, when you take the thermodynamic properties inside region 0, you can compare that against experimental data. The other thing that you can do is, depending upon the region, you can either increase the mesh resolution or go for a lower mesh resolution. This is really important because depending on the type of problem, there are certain regions where you don't need a lot of computational cells. A fewer number of cells is enough. For example, in an engine, you need to make sure that To capture the flame front, you need to have really small cells, and having multiple regions or having a separate region for the combustion chamber helps us set this up. And then there is something called as mapping the solutions, which you can think of it as initialization, but the only difference is that mapping is done based on the results from a different simulation. So for example, say that someone has already run a simulation using a different software, or you have experimental data that contains the pressure and temperature value at each XYZ location. That is what you call as a map file. You can take that map file, and with that you can provide better initial conditions for your entire simulation. If this point is not clear, let me know and I'll explain it. Finally, you can specify combustion models by regions, and you can also provide a region specific CFL number. This point is going to be much more clear when we talk about CFL number and what it does. Okay, that being said, I would like to conclude this theory lecture. I know that we covered a lot of topics. If you have any questions, please let me know and I would be happy to answer that. Thank you. Bye.